So the last thing to talk about in this section are distributions. So what distributions do? What are we doing? Well, we're kind of getting an idea about this when we put a frequency table together. And a very powerful tool to see the distribution of our data is the histogram, which we saw earlier. So we're looking to understand how data is distributed across categories. Now, we talk about distributions, it's not necessarily just categories we're looking at. We'll talk about some other distributions later on where we're looking at how data is spread across an interval. But for now, we can think in terms of categories, whether we're thinking maybe our, the intervals that we saw earlier for temperatures, for example. How's the data spread across those? So let's take a look. Now, a common distribution is called the normal. And this is a common one that comes up a lot. And there's a lot of uses for this distribution. But basically, it has these kinds of properties. The frequencies, they start out kind of small. And then they'll increase. And what the text says, they'll increase, say, to 1 or 2 highest values. And then what they're going to do, they're going to then decrease to smaller frequencies again. So they start small, they increase until you get 1 or 2 highest frequencies, then they decrease the smaller frequencies again. So an example, and we'll take a look at our McDonald's example. We have times in the drive-through, and then we had our frequencies. So let's take a look at some frequencies here. Let's say we have 2, 8, 30, 8, and 2. So what we see is we start out kind of small, then we're increasing, and then we hit a high frequency, and then we're decreasing again. So this would be approximately normal. So approximately normally distributed. And if you were going to do kind of a rough histogram, so this will be our first, second, third, fourth, and fifth. I'll just call them this for simplicity's sake. I'm going to run out of room, I think, down here. But for that first class, frequency got up to 2. That second class got up to 8. And these are going to be, well, not drawn to scale because of space reasons. Call this 8. So definitely not drawn to scale, but 30 up here. Our third class, frequency of 30. And then our fourth was 8 again. Then our fifth class was 2. And usually what I'd want to do is I'd want to write the interval here like 75 to 124, but for space reasons, I'm just using this alternate labeling. But the thing that we're going to notice, it has what's sometimes referred to as a bell shape, or a bell-shaped curve. And this is very characteristic of a normal distribution. And it's approximate, it's close enough. Real data, you're not going to get a perfect fit. Usually not, as the author says. So when we look at our normal distribution, is data distribution close enough? I'll abbreviate distribution. And then again, real data is not so perfect. But close enough, close enough. So the last bit in this section, it's sort of a reflection on data. Is there anything we can learn from the data other than distributions? Because we're getting into this, we'll get more into distributions later on. But it turns out, looking at frequency charts, looking at the frequencies of categories, well, there's actually something else we can do. And it has to do with creating another frequency chart for the data itself, that looks at the data, the characteristics of the data. So we're going to study the characteristics. So first thing, analysis of last digit of numeric data. So this might seem kind of unusual, but we collect our data and then we look at the last digits. And that's going to be, the last digit could be a 0, 1, a 2, a 3, and so on, up to a 9. And we want to see how often these 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, how often each of those numbers appear in the last digit of our data. And this is what this can do for us. It may suggest how the data was collected. It may suggest how it was collected. This might seem kind of strange, but here's the example that they give. Let's say you have data that's 2,219 adult pulse rates. And what we're going to do is create a chart, which is the frequency of the last digits in each of these pulse rates. So if you have a pulse rate of 103, and pulse rates are usually measured across 1 minute. So after 1 minute, you have a pulse rate of 103, then the last digit of your pulse rate would be a 3. And so the last digits, well, it's going to be 0 through 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And so how often did 0 come up as a last digit? So this would be like a pulse rate of 80 or a pulse rate of 90 or 100. Well, this came up in 455 pulse rates. Again, this is frequency. I'll abbreviate frequency. The number 1, 0 times. In this data, they did not record a pulse rate of 81 or 91. So 2, how many times did 2 come up? Well, 461. But 3 came up 0. 4 came up 479, so maybe someone had a pulse rate of, well, 84. 5 came up 0 again. Excuse me. 6 was 425. 7 was 0. 8 was 399. But 9 was 0. So what's going on here? Well, basically, here's the pattern. There are no odd number in the last digits. No odd number. Well, that's strange. Like, are pulses required to always be even numbers per minute? What governs that? Well, have you ever taken like a CPR class or an EMS class, what you'll learn about pulse rates is that often what people will do is they'll time the pulse not for the full minute, but for just 30 seconds, and then multiply by 2. Another technique is to time the pulse for 15 seconds and multiply by 4. And there's various reasons for this. Maybe it's just not good. Can you sit there for an entire minute? You're not in a position where you can do that for some reason, and you want to collect vital signs as quickly as possible. Now, the author makes a note that the data did not appear to result from multiplication by 4. The data did not result from multiplication by 4. So what this might suggest, the reason we only have even numbers in the last digit, well, when you take any number, whether it's odd or even, and multiply by 2, you get an even number. So even numbers, multiplication by 2 always creates an even number. So what's probably going on here is this. Based on looking at the frequency table of last digits, seeing that there are no odd number last digits and only even number, that must mean if all the pulses are even numbers, because even numbers will have an even last digit. Odd numbers will have an odd last digit. So since all the last digits are even, and it doesn't look like any of these are multiplied, the result of multiplication by 4, it suggests that what was going on is that whoever's collecting the pulses was collecting them for 30 seconds. And after 30 seconds, you'll get an odd number, even number of pulses. Remember, pulses are supposed to be for the entire minute. So what you'll do is you'll collect 30 seconds of pulses and then just multiply by 2. So if they got an even number of pulses in 30 seconds, they'll multiply by 2 to get an even number for the entire minute. If they get an odd number of pulses for that first 30 seconds, well, they'll just multiply it by 2. Multiplication by 2 will also give you an even number. Odd times even gives you even. So odd times 2 will give you an even number. So again, you'll get an even number for the entire minute of pulses. And then multiplied by 2. So that's probably what's going on here. So you might discover by looking at the last digits how those are distributed, that there's some mathematical pattern or some process going on that's in your data collection. So had some influence on your data collection. So that would be an example how looking at the last digits could tell you how the data was collected or just organized, how it was handled. And well, there you go. Let's take a look at another one. So other things you can maybe infer by looking at your data. So this one here, we didn't actually look at the data to make this conclusion. Well, I guess at some point we had to. We had to count up how many last digits were odd and how many last digits were even, or let me go back, how many last digits ended in a 1 or a 3 or a 5 and so on, how many last digits ended in a 0 or a 2 or a 4 and so on. And then we constructed a frequency table. Here we're just going to look at the frequencies of our data. And we're going to look for what I call gaps made of zeros. So gaps. And here we're not talking about the gaps, say, between classes necessarily. We're talking about zero frequencies. So here the data could suggest, the data is from more than one population. Now the example we're going to look at is from possibly 2 populations. So let's say we're looking at this. I need to erase this, get a little more room. So let's say you go to the bank and you ask to get some rolls of pennies, and you're going to look at the weights of pennies. In any manufacturing process, there's always slight deviations from like the desired amount. You know, we try to make everything the same. If you go to, say, McDonald's, the burgers, a certain type of burger should be the same at the McDonald's on the north end of town as it is the same as the burger from the south end of town. Same as the burger that's in Albuquerque. Same as the burger in Las Cruces. But there's going to be a little bit of variation. So we're going to take a look at penny weights and see, kind of what are pennies weighing generally. And so let's say we have this. And so we go, this is going to be in grams. So 2.50 to 2.59, 2.40, 2.49, 2.50, 2.59, 2.60, 2.69, 2.70, 2.79, 2.80, 2.89, 2.90, 2.99, 3.00, 3.09, and then finally 3.10, 3.19. And then I'll abbreviate frequency. So there we go. So what are our frequencies? Well, 18 were 2.4 to 2.49, 19, excuse me, 2.50 to 2.59, and then we have 0, 0, 0, and then 2, 25, and 8. So what the author was saying is that when you have these zeros, this is the gap that we're thinking of. For some reason, we're getting frequencies on the low end and frequencies on the high end. And what the author is saying is this could be indicative of two different populations that we're looking at here. And the author makes a note. What are these two different populations? Well, we're collecting pennies. I mean, it's there's one population of pennies out here. Well, you could think of it as two different ones, and we're actually sampling from them both, maybe not realizing it. So this is what the author notes. So pennies before 1983 were 95% copper. I'm going to use Cu, stands for cupric. It's it's a alternative name for copper. And then 5% zinc. So before 1983, pennies are mostly copper, a little bit of zinc. After 1983, pennies were 2.5% copper, cupric, and 97.5% zinc. So what happened? Pennies before 1983 have a very different balance of composition, far more copper than zinc, which is not what happened after 1983, where now very little copper and a whole bunch of zinc. And what we could be seeing is a distribution here where one of these populations is before 1983 pennies, And the other collection of frequencies, I should say frequencies, one collection of frequencies here is for pennies before 1983. The other frequencies are for pennies after 1983. And so we could actually have two different groups here with some different characteristics, and that's why we're getting this separation in the frequencies. And we can see that separation because of the zeros. All right. The last thing to mention here, it's really just a way of analyzing or comparing. And it's a neat way to do it. We can, in a sense, combine our frequency table. So we put two or more relative frequencies in the same table or same chart. Now, they mention relative frequencies. Why not just put frequencies? Well, what we're going to do, we're going to combine results from two different studies. And the thing is, it depends on, well, the relative frequency kind of, it makes it maybe easier to compare. I mean, you could probably add up the frequencies and see the total. And, well, you could kind of tell, is this a significant amount of frequencies or not, given the total. It might be easier to report that as a percent initially. And instead of having people have to count up all the frequencies, get a total, and then, you know, how does this one compare to the total? And depending on how the distribution goes, that might not be so bad. So let's say we have this. So let's say we're going to take a look at lunch service times. And it's going to be McDonald's versus Dunkin' Donuts. So again, we're going to do this in seconds. So here's McDonald's, and here's Dunkin' Donuts. So here are the frequencies, relative frequencies for McDonald's. So what we can do, we can compare the relative frequencies, the results from each of these studies. And this makes it a little easier to compare McDonald's versus Dunkin' Donuts. And so we can see that, you know, if the McDonald's, we got most of our time here, the most common time spent is 125 seconds to 174. So just over 2 minutes to just under 3 minutes. Again, divide these by 60 to turn into minutes. For Dunkin' Donuts, it's mostly this gap here, this interval, so just over a minute to just over 2 minutes. And so this kind of gives you, a way of comparing things, a little easier perhaps. You're not going from one chart to the other. And then it's got everything kind of lined up. You can see that Dunkin' Donuts, the frequencies tend to be on the lower end for the times, and McDonald's tends to have theirs on the higher end, though not by much. And well, that's the idea. So that's going to be it. If you have any questions, let me know.